Hello, my shimmering stars. Today, I, Shaurya Grover, welcome you all to this amazing platform of PW English. Students, today we are going to start with lecture number 2 based on the chapter Coordination Compound under our batch Excellence Batch. I hope so you have seen the previous lecture and all the concepts were clear to you. So, today we are going to start with our very new topic and important topic, that is going to be the hexadentate ligand. I hope so you have seen the previous session, and in that particular session we were now familiar with the terms such as ligands, central metal atom, denticity, right? So now you all are aware of these terms. Great. So students, we were classifying the ligands based upon the denticity, and we got to know about monodentate ligand, bidentate ligand, tridentate ligand. So we are going to move on with the next topics from that segment, right? So let us start over this segment with a beautiful smile. So students, what are the topics that we are going to cover in this particular session? So first of all, students, we are going to study about tetradentate ligand, and also about hexadentate ligand. Tetradentate ligand and hexadentate ligand. Then students, we are going to study about flexidentate ligand and the chelating ligands. Then we are going to see about flexidentate ligands and the chelating ligands. Further students, we are going to proceed towards the oxidation state. And the coordination number. Oxidation state and the coordination number. And the most important topic then we are going to do is naming of coordination compounds. Naming of coordination compounds. So students, let us start with the very first segment, that is basically about tetradentate and the hexadentate ligands. So if I talk about hexadentate ligands, or let us first talk about the tetradentate ones, right? Yes, first of all, okay, I shall divide this into two halves so that we can make both of them, okay? So here you can write about tetradentate ligand. See, tetradentate will be one in which the denticity is going to be what? The denticity is going to be 4. Tetra refers to as 4. That means there will be 4 donor atoms present in the particular ligand. Am I right? Now, if I give you an example of tetradentate ligand, we can take an example of triene. Now, what was En? En is basically what? You have seen this in the bidentate as well. Do you remember this? Yes. So, we are going to repeat this En, basically ethylene diamine, 3 times. Then it will form what? It will form triene. What is En? Ethylene diamine is En. Now, when I am going to repeat it 3 times, it shall form triene, right? Now, see how I am going to repeat it 3 times. See this structure basically over here. This is first time, second time and third time I am repeating it out, right? And let us say that we have central metal atom over here. So this nitrogen basically has lone pair of electrons. So we have a tendency, let me show with another color. So first tendency is that this nitrogen atom can donate its electrons. Similarly, this nitrogen and this nitrogen. So here are 4 donor atoms. That's why it lies under the category of tetradentate ligand. Is it clear to you all? Now students, moving on to the hexadentate one. In hexadentate, the most important and the famous example is EDTA. Which one? It is EDTA. It is EDTA. What it is? It is EDTA. Ethylene diamine tetraacetate. What it is? Ethylene diamine tetraacetate. You can even write it over here. Ethylene diamine tetraacetate. Now we shall draw its structure over here. See, in order to make EDTA, it is very simple. As you are writing diamine, basically ethylene diamine is what? Ethylene diamine is NH2, CH2, CH2, NH2. Now, if I am going to replace both of the hydrogens with acetate ion, then I am going to get what? I am going to get ethylene diamine tetraacetate. What I have said over here, first of all, draw ethylene diamine, which is this, right? Now, replace the hydrogens with the acetate ions, right? Here there are two hydrogens. Similarly, here are also two hydrogens. So, we have to replace it with acetate ion. Now, what is acetate ion? It is CH3 C double bond O negative. Now, when I'm going to replace it, right, and when I'm going to write it over here, so now many of you may think that, ma'am, over here, why you have not written CH3? Why you have written CH2 over here? Kindly explain. See, we have to see the valency of carbon as well. Carbon will make only 4 bonds. So, one bond over here, another bond over here, and 2 bonds with hydrogen atom. It cannot form 5 bonds, yes? So, that's why I've written CH2. I have not written CH3. So, now this is the structure of what? EDTA. Let us say that we have a central metal atom over here. So, in this particular structure, which are the donor atoms that are going to donate its electrons? Number first, these two nitrogens. They will donate the electrons because they have lone pair of electrons over them. And then is this oxygen atom, this O negative as well as this O negative. So how many donor atoms are present over here? Total 6 donor atoms are present over here. Hence its denticity comes out to be what? Its denticity comes out to be 6. And it lies under the category of hexadentate ligand. I want you all to write it down so that we can move on to our next part. I'm giving you all a minute. Kindly write it down so that we can move on to our next part. I hope so. You all have written. Over here, these arrows are representing that lone pairs are being donated to the central metal atom. Is it clear to you people? Great. Now students, this was about tetradentate and the hexadentate ligand. Now we shall move on to the ambidentate ligands. Now ambidentate ligands are the one which basically have 2 donor sites, but eventually only one will donate at a particular time. So these are the ligands which can donate through either of the 2 different atoms present in that particular ligand, right? As I've said you, they have 2 donor atoms. Okay, a particular ligand has 2 donor atoms, but only one will be donating its lone pair of electrons at a certain time. Any one of them can donate, so it is referred to as ambidentate ligand. Okay, so you can even mention over here which can donate from either of the 2 atoms present in a ligand. These are referred to as ambidentate ligands. If I talk about their examples, students, cyanide, isocyanide. Okay, in one of the following, carbon is donating, in another one nitrogen is donating at a particular time. Similarly, NO2 negative and one is ONO negative. In one of the following, nitrogen is donating and in the another one, oxygen is donating its lone pair of electrons, right? Similarly, you have the structure over here. You can write it in such a way also, like this. It is the same thing. Okay, so what it is? It is thio. cyanate and it is isothiocyanate, right? So in one of the following you can see that over here also one atom is donating at a particular interval of time. Both will not donate together, only one will donate. They can, either of them can donate. Okay, on the basis of this, these are referred to as what? Ambidentate ligand. Is it clear to you, students? Now students, before moving on to the next part, that is what is flexidentate and chelating ligands, first of all I want you all to understand what is oxidation state and what are the formulas, so that you will get to know about charges. I want you all to understand about charges, then only you will be clear with the term flexidentate, right? So before going on to that, how can you represent a formula for coordination compound? Just as I've told you in the previous lecture that we used to represent coordination compound in the in this particular coordination sphere or the coordination entity, right? And the ions which are present outside are referred to as ionizable ions. The ions which are present inside are referred to as non-ionizable ions. Other than this, I told you that there is a central metal atom M over here which is bonded to some ligands, let us say L, and the number of ligands are represented by X over here, or you can say N over here, right? These are number of ligands, and over here plus minus X is written, that it is the charges. It can be a positive charge, it can be a negative charge. Here was A written, A positive, here was B negative, which are the ionizable ions. So this is basically the representation. That is all written over here. I shall read from the NCERT. What NCERT says: the formula of a compound is the shorthand tool which is used to provide the basic information about the constitutions of the compound in a concise and convenient manner. So what does it explains over here? That whensoever we are writing all the elements all together, such as central metal atom, ligands are bonded, so we are basically representing them in a very concise form. Great. Now see, what are the basic rules that we have to follow in order to write the formulas? So the very first basic rule is the central atom is listed first. The central atom that you are writing is listed first of all. Then the ligands are then listed in the alphabetical order. Now when you're going to do the naming as well, students, you shall be seeing during the naming of a coordination compound, we are writing the name of a ligands in alphabetical order, such as the ligand which starts with A and ligands which starts with E. So A, the one will be written first and then the E one will be written. The placement of the ligand in the list does not depend upon its charge. Okay, the placement doesn't depend upon charge, it depends on its alphabetical order. Next, polydentate ligands are also listed alphabetically. Now polydentate, which have a denticity more than 2. It can be 3, that is tetradentate, that is 3 tridentate, 4 is tetradentate, then is hexadentate. So they are also written in alphabetical order. In case of abbreviated ligand, the first letter of the abbreviation is used to determine the position of the ligand in the alphabetical order. So they can also determine the position, right? Next things, the formula of the entire coordination entity, whether charged or not, is enclosed in the square brackets, which I have already told you. Yes, when ligands are polyatomic, their formulas are enclosed in parentheses. Ligand abbreviations are also enclosed in parentheses, right? Next is, there should be no space between the ligand and the metal within a coordination sphere. They are written all together. There is no space, okay, that we have to put inside. When the formula of the charged coordination entity is to be written without that of the counter ion, the charge is indicated outside the square brackets as the right. See, as I've told you, this is the charge which is written on the right hand side. Okay, as the superscript with the number before the sign. Okay, number sign should be written before the number. For example, we have this over here, as you can see, CO, then we have CN, then we have 6 and the charge is -3. Okay, one more thing, students, one more thing, you can write it as C. Number before the charge, number before the sign, like this way. This is the correct representation, though in some of the cases you shall see -3, but this is the correct representation. Next is this, you can see over here there is +3 charge. The charge of the cation is balanced by the charge of the anions. Yes, okay. Now these were the things that you need to know. Now comes the oxidation state, which is a very, different topic and a very important topic as well, because this will let you know about the charges, right? So what is basically an oxidation state or an oxidation number? Those students, you have seen this particular topic in your redox reaction chapter also in class 11, but that was related to some of the compounds. While if I talk about the coordination compound, oxidation state is really very important topic. Oxidation state is basically the formal charge on any atom. Any atom which holds any charge is referred to as its oxidation state or the oxidation number as well. Or in other terms, I can say the number which represents the electrical charge, okay, on the central metal atom. So let us read the definition. Oxidation number of the central metal atom, what it is. The oxidation number of the central metal atom is in a complex is defined as the charge it will carry if all the ligands are removed along the electron pairs that are shared with the central metal atom. Or if you want to write the different definition with regard to this only, you can even mention it that the number which represents charge on central metal atom is referred to as its oxidation number or the oxidation state. Now one more thing, whenever you are writing oxidation number in a particular, you're doing a naming of the coordination compound, then you need to represent the oxidation state or the oxidation number in Roman numerals. Okay, for examples, they are saying the oxidation number is represented by Roman numeral in parenthesis following in the name of the coordination entity. For example, the coordination number of copper in this particular case is +1. Let us say it is +1. So it is written as 1. Like this in brackets. If for example we can say that the coordination number, sorry, oxidation number, not the coordination number, kindly correct it out, okay, by mistakenly I spoke that. I'm talking about oxidation number. If oxidation number or the charge comes out to be 3, so it shall be written in Roman numerals. If it comes out to be 4, it shall be written like this. Is it clear to you all? Now when I will be giving you certain examples, you will automatically get what I am referring to as. Now let us see how to calculate oxidation state in the following compounds. Let us start with the CO2. For example, over here, as I've told you, oxidation state will be calculated for the central metal atom. So central metal atom over here is carbon. So in order to calculate for carbon, we shall assume it as X. Now, what is the basic rule in order to calculate the oxidation number? You need to add all the oxidation states or all the charges of all the atoms present in that particular molecule. For example, over here we have carbon, so it's, let us say we don't know its charge, so it is referred to as X. Now, oxygen we generally know, generally the oxidation state or the charge present on oxygen is -2. Okay, how many oxygen atom? 2 oxygen atom. This basically, the sum of all the oxidation states or the sum of all the charges that are present on the atoms in a compound is equivalent to 0 until and unless any charge is provided over there. In some of the cases, you shall be seeing that there is a certain charge over here. So that their sum shall be equivalent to that charge. But if it is not mentioned over there, students, then the sum shall be equivalent to what? 0. Now let us see what is the oxidation state of carbon over here. It is X minus 4 is equivalent to 0. Now when we will take this negative sign onto the another side, the sign will get changed and we shall get X as equivalent to +4 automatically. So over here the oxidation state for carbon comes out to be what? +4. Is it clear? Now let us see this particular example over here that we have. Over here, what is the central metal atom? Now you know, basically I've just told you right now how to represent a coordination compound or how to represent the atoms present in the coordination sphere. First of all, central metal atom is written and then ligand is written. That means Fe over here is your central metal atom. Am I right? Now you have to calculate its oxidation state. How you will calculate? This is very basic, simple formula. There are two ways in order to calculate for this particular. Let us see. See, potassium, basically we know it has a +1 charge. We know this thing. So potassium has +1 charge because it is, it is the group 1 element. Now, how many potassium? 4. If you don't know, you can write it over there. It has a +1 charge. How many potassium? 4 potassium. Plus, for Fe, we need to calculate. So, we shall assume it as X. Plus, for Cn. Cn basically has a -1 charge. If you don't know, I'm telling you. Okay. It has a -1 charge. How many Cn? 6. Now, the sum shall be equivalent to what? 0. Yes? What you will get? 4 plus X minus 6 is equal to 0. X minus 2 is equivalent to 0. When we will take this negative sign over there, we shall get X is equivalent to +2. So the charge on Fe comes out to be +2. This is the first way that you can do. I am letting you know another way also. There is two ways to solve this question. Or students, as you all know, this is the very initial method. You will add all of them all together and the sum shall be equivalent to 0. One more method is that just split them into its ions. Just split it into its ions. If you split this into its ions, you know, K positive will separate out because it is ionizable ion. If K positive is separated out, how many K positive? 4 K positive. Plus, this coordination sphere will be separated out. What is inside it? Fe, Cn6. If it has a +1 charge and 4 are there, so +4 charge, then this will have -4 charge because it should be balanced. See, again I'm telling you, if you are splitting this particular species over here, you know that it is a neutral species. Over here, if it has a K plus charge, 4K are present, so 4K positive. So this shall have how many charge? -4 charge. Now you need to calculate the oxidation number for whom? For Fe. So what will happen over here? X plus, for cyanide, you know it is -1 into 6 is equivalent to what? It is equivalent to the charge that is present over here. Okay, so either you can do in this form. So what you will get? X minus 6 is equals to -4. Am I right? Now take this over there. What you will get? X is equals to -4 plus 6. That comes out to be +2. So these are the two ways that you can solve this particular question. There are two ways in order to solve this question. Okay. There are two ways in order to solve this particular question. You can follow either of them. This is basically the simplest. You'll add all of them together, or you can just dissociate them into its ions. It will not get separated because these are the non-ionizable one. But yes, it will get separated. So its role is finished because its role was to initiate charge on that, so that your sum shall be equivalent to that. I told you, if there is no charge given, you shall take it as 0. But if there is something charge present over there, then their sum shall be equivalent to the charge. Is it clear? Is it clear? Kindly write it down, students, so that I can move on to the next questions over here that we have. Kindly write it down. Okay, now we have this particular question. Again, what is the central metal atom? Ma'am, the central metal atom is CO. The central metal atom over here is CO. So now let us start over here. Again, see, basically, 1 second. This is not present over here. Yes, it is like this. So either if you dissociate them, you know basically it has a +1 charge. And there is only one K positive, so it will have -1 charge. So separate it out, you will get only this K positive is separated. Either you take it all together or you can differentiate it. So I am just solving which one? CO, NH3 twice, Cl2, SO4 -1. And K positive is separated out. So just cancel it out. Now solve this all together. For CO, let us say it is at X. Now for ammonia, NH3, do it have a charge? No, it is neutral. So 0 charge into 2 plus, what is the charge on Cl? Halogen atoms has charges of -1. How many halogen atom? 2 halogen atom. Plus, what is the charge on SO4? Ma'am, it is -2. Now all of them will be equivalent to what? -1. Because this is the charge that is initiated by the K positive. See, in any of the species, cation is written first, anion is written afterwards. Is it clear? Now, what we will get? X plus 0, -2 is equivalent to -1. X minus 4 is equivalent to -1. X comes out to be -1 plus 4. That is +3. So, the oxidation state comes out to be what? +3. Is it clear to you? Great, students. Now, we have... Which color should I take? I've taken all the colors. Okay, we have this question as your homework. Let us say it is your question number first as your homework. Okay, you have to tell its oxidation state. Shall we move further, students? Great. Now comes the next question on the oxidation state as well. Again, see, I'm going to do with both of the methods if you feel okay. Now over here, this is directly written. Okay, over here, see, basically, if you are taking all of them together, so we know that potassium has +1 charge. How many potassium? 3 potassium. Plus Fe charge we need to calculate. Plus Cn has -1 charge into 6 is equivalent to 0. This is the first method. So +3 plus X minus 6 is equivalent to 0. X minus 3 is equivalent to 0. X comes out to be +3. Either you can solve in this manner, or you can do in such a way that you are dissociating them, and it will dissociate into 3K positive and into FeCN6. What will be the overall charge? If it has +3 charge, it will have -3 charge. So now you need to calculate for this. It is X plus Cn has -1 charge into 6 is equivalent to -3. X is equals to -3 plus 6, which comes out to be +3. So you can solve in either of the two ways in which you feel it is fine. Great. Now let us see the next question that we have over here. Again, we are letting CO as X. For again, fluorine, we have fluorine comes under the family of halogen, so it will have -1 charge. How many fluorine? 6. So -1 into 6 is equivalent to -3. So X minus 6 is equals to -3. X comes out to be -3 plus 6. That means X comes out to be +3. Is it clear to you, students? Kindly write it down. Now this is the most important one. This is the most important one. Let us see. See over here what is happening. For Fe we need to calculate. What is the charge on EDTA? We have just done right now. See. The structure for EDTA, let me open the structure for EDTA, it will be clear to you. EDTA has how many charge? See, -1 charge over here, -1 here, -1 here, -1 here. That means EDTA has basically -4 charge. How many charge? Ma'am, -4. EDTA has basically -4 charge. Is it clear to you all? It is very important. How many EDTA molecule? 1 is equivalent to the overall charges -1. So x -4 is equivalent to -1. When this will go on the other side, it will become positive value. X is equals to -1 plus 4, that is +3. So the oxidation state on iron comes out to be what? +3. Let us see the next case that we have over here. In the next case, let us say this is the central metal atom. So we are assuming it as X. Now for Cl, you know, halogen, so it is -1 into, now you have what? Basically you have NO2 over here. Students, over here now in this particular C, we have two ligands. We have how many ligands? One is Cl, one you have Cl with you over here, one you have NH3, which are 4, and one is Cl. Cl has -1 charge. Similarly NO2 has -1. I have written multiplication sign will not come. It is -1. Then for ammonia, we know it is 0 charge. It is equivalent to the overall charge, that is +1. So x -2 is equals to +1. This will go on the other side. X is equals to +1 plus 2. That comes out to be +3. Is it clear to you? So over here, the oxidation state comes out to be +3. Kindly write it down, students. Kindly write it down, students. Okay, there are now some questions based upon the coordination number and the oxidation state. As I've told you, I shall let you know about coordination number as well when we'll talk about oxidation state. So my question for you all is, in this particular question, FeEDTA, overall charge -1, what is oxidation state and coordination number? What is oxidation state and the coordination number? Basically, coordination number is the number of donor atoms, I would say, okay, present over there. So see, over here what is happening? Over here, oxidation state you have just calculated. For Fe, you let it as X. For EDTA, the charge is -4 and it is equivalent to the overall charge -1. X is equals to -1 plus 4. X comes out to be +3. So oxidation state, or OS, I can write it as +3. Right? Coordination number. Coordination number, as I've told you, depends upon the number of donor atoms that are present over there. Right? So over here in the case of EDTA, you have just seen. See, in the case of EDTA, how many donor atoms? 1, 2, 3, 4, 5 and 6. 2 nitrogen and 4 oxygen. Yes, so the coordination number for this comes out to be what? It comes out to be 6. Is it clear to you? Now one more question based upon them. See the next question. The next question is coordination number of CON COF6 minus 3. What will be the coordination number over here? So as I've told you, coordination number is basically the number of donor atoms that are present in a particular compound. So we know that CO over here is what? It is central metal atom. It is what? It is central metal atom. Am I right? Yes, ma'am. What is F over here? Ma'am, these are ligands. Now, ligands are basically the donor atoms, right? How many ligands are there? Ma'am, 6. So, the coordination number comes out to be what? 6, because the donor atoms present over here are 6. Is it clear? Okay. Now, bringing more questions for you. The next question is... okay. Yes. PT En twice, charges +2. Calculate oxidation state and the coordination number. Okay, students. Now see, basically if we are going to calculate the oxidation state over here, what do we have? We have platinum. For example, we let it as X. For En, do it has a charge? No. Ethylene diamine has no charge. So 0 into how many ethylene diamine? 2 is equivalent to what is the overall charge? plus 2. So X comes out to be plus 2 because this is 0, right? So the oxidation state, ma'am, comes out to be plus 2 over here. Now question arises for coordination number. Coordination number is number of donor atoms. What is the structure of En? En basically is ligand. That means we shall be talking about ligand. Let us draw this ligand. This ligand is basically NH2, CH2, CH2, NH2. Am I right? Over here we know that nitrogen basically donates the lone pair of electrons to the central metal atom. Right? So how many donor atoms in one En? In one En there are 2 donor atoms. How many En are present over here? 2. So if in one En 2 donor atoms are there, in 2 En how many donor atoms? 4. So the coordination number comes out to be 4. Now many of the students basically they do this question wrong. Why? Because they think that En is written and it is 2 written. So 2 ligands are there, so 2 donor atoms. No. Open the structure for En and see there are 2 donor atoms in a single En. Ethylene diamine holds 2 donor atoms. So 2 ethylene diamine will hold 4 donor atoms, hence the coordination number comes out to be 4. So the correct definition for coordination is number of donor atoms present in a ligand. Is it clear to you, students? Okay. Now after this I shall come back to my topic, that is the flexidentate ligand. Now you are aware of the term, that is charges, right? Now flexidentate ligand are the ones which have a variable denticity, which shows variable denticity. Which shows what? Variable denticity. How can I say that? Let us take an example of EDTA. EDTA has what charge? -4 charge. Am I right? Now what is the structure for EDTA? Again, first of all, draw ethylene diamine. Right? Now replace the hydrogen atom with the acetate ions. CH2, C double bond O negative. Over here again CH2, C double bond O negative. Now see over here, it is CH2, C double bond O negative. Again over here CH2, C double bond O negative. Now look over here, students, the thing that you need to understand, it has overall charge of -4. What is the denticity when we talk about EDTA? The denticity over here, ma'am, is basically 6. Why? Because there are 6 donor atoms, 4 O negative and 2 nitrogen. Okay. Now what shall I do if I replace one of, if I add one hydrogen over here? See how does O negative arise over here? Initially there was OH. When H positive went off from here, O negative charge came, right? So basically if I insert one hydrogen, then the structure will be HEDTA. What will be the charge on that? If I'm adding one hydrogen in the EDTA structure, it comes out to be HEDTA. What will be the charge now? -1, -1, -1. Ma'am, -3 charge. Okay. Now what shall be denticity for this case? What shall be the denticity for this case? Ma'am, denticity is number of donor atoms. Now when we are adding one hydrogen, then this oxygen won't donate any electrons. This will donate, this will donate, this will donate, and 2 nitrogen will donate. Ma'am, denticity comes out to be 5. Okay. Now if I add one more hydrogen atom over here, that means H2EDTA. What will be the overall charge? Ma'am, -2 will be the overall charge. Okay, what will be the denticity? Ma'am, now only 2 nitrogen and 2 oxygen will donate. So denticity will be 4. So now this means that when a certain ligand has a tendency to show variable denticity, it is referred to as your what? It is referred to as a flexidentate ligand. Is it clear to you people? Great. Now students, next comes out to be chelating ligands. If I talk about chelating ligands, see basically bidentate or polydentate ligands which attach themselves with the central metal atom in such a way that they are forming a ring. That is referred to as a chelating ligand. Chelates, that means ring we are talking about. Okay, so we can say that bidentate or the polydentate ligands which attach themselves to the central metal atom in such a way that they form that it forms ring, or we can say chelates, are referred as chelating ligands. Are referred as what? Chelating ligands. Bidentate or polydentate ligands which attach themselves to the central metal atom in such a way that they form rings. Okay, now how to see how many rings will be formed? Number of rings is equivalent to denticity minus 1. Let us take take an example. Ethylene diamine. What is the denticity over there? It is 2 because there are 2 nitrogen atoms that are responsible, minus 1. So 1 ring will form over there. How come? See, it is CH2, CH2, NH2, NH2. Now we know that NH2, NH2 are making a bond with central metal atom in such a way that they are forming a single ring. How you can check it? Number of rings is equals to denticity minus 1. Is it clear to you people? Yes. Shall we proceed to the next part? Now students, we are going to proceed towards the naming of the coordination compound. Okay, now we are clear with the terms oxidation state, we are clear with the terms coordination compound. Now we shall start with our naming of coordination compounds. How shall we name a particular compound? This is the most important thing. See, now these are the lines that I've taken from NCERT, and I'm going to add some of my points over here that you can even write in your NCERT, or if you're making notes, you can write it over there, right? So the name of the coordination compounds are derived by following the principles of additive nomenclature. Thus, the groups that surround the central metal atom must be identified in the name. First of all, you have to identify the central metal atom. Next, they are listed as prefix to the name of the central metal atom along with any appropriate, first of all, you have to identify about the ligands that are surrounding the central metal atom, and the ligands name are basically written as a prefix to the central metal atom. First of all, you shall name the ligands and then you will name the central metal atom. Do remember this order. Initially, you know that central metal atom is surrounded by ligands. So when you are writing the nomenclature, first of all, write the ligands name and then the central metal atom name. Is it clear? Now next is, the following rules are used while naming the coordination compound. What is the very initial, the basic rule that you need to remember? The cation is named first in both positively and negatively charged coordination entities. You have to name cation first, then you have to proceed further. For example, if you remember in simple salts, if you know, what is NaCl? What is NaCl? In terms of Na, you know Na holds positive charge, Cl holds negative charge, cation is Na. So you write sodium, no? First, initially you write sodium. Similar happens in the case of coordination compound. The cation shall be named as first. For example, if you have a certain compound as K4, FeCN6. For example, we have this thing. Now you know the charges over them. Yes, ma'am, we know. Potassium holds +1 charge, ma'am. And if it is 4 potassium, it will hold -4 charge. That means this is the cation, so it shall be named first. So we know that it is named first. So its name is potassium. There is no need to write 4 potassium. No. The ones that are present outside the coordination sphere, their numbers are never mentioned. Never mentioned. They are just write it potassium. Or if we have sodium over here, you write sodium over here, right? Now we shall see the second rule that is given to us. The ligands are named in alphabetical order before the name of the central metal atom. First of all, you shall name the ligands, and that also you have to name in alphabetical order. For example, we have a certain ligand as chlorine and we have a certain ligand as bromine. Basically, chlorine is written as chloro or chlorido and bromine is written as bromo or bromido, right? So you have to see A, B, C, D, like B comes first. So you have to mention bromine first initially in comparison to chlorine. First bromine will be written, that means bromo or bromido will be written, and then chloro or chlorido will be written. So you have to follow the alphabetical order, right? Right? Is it clear to you? Now students, next comes out to be the names of the anionic ligands end in O. Those of the neutral and the cationic ligands are same. Now see, basically, as I've told you, the anionic ones, for example, we have Cl negative. Basically, it is what? It is chlorine, no? Or we can say it is, we write it as chloro. Bromine is written as bromo, like this way, okay? So it ends with O. Now I will give you some of the examples over here, you'll automatically get it. See over here. Anionic ones. Chloro, chlorido, ending with what? O. Bromo, bromido, ending with what? O. Cl negative is chloro, chlorido, written as chloro, chlorido. Br negative is written as bromo, bromido. Cyanide is written as cyano, ends with O. Negatively charged, anionic, no, that's why. So basically, if the ligand is O2 negative, again anionic one written as oxo or oxido. OH negative is written as hydroxo, ends with O, right? More examples if you want to see. H negative is written as hydrido, ends with O. Next is C2O4 minus 2 is written as oxalato, ends with O. Next is NH2 negative, amido, ends with O. NH2 power is minus 2, imido, ends with O. Okay, these are the anionic one. While if I talk about the neutral and the cationic one, they are written as it is. For example, if I talk about CO carbonyl, NO nitrosyl, H2O aqua, NH3 amine. Now one more thing. In amine, you have to write double M. Don't forget this. Okay, first of all, write the list so that I can move on to the next page and show you the next list. Okay. First of all, write the anionic one, then come to the neutral one. Okay, one more thing. In the neutral one here, C5 will come. Yes. C5H5N, pyridine, then CO carbonyl, NO nitrosyl, H2O aqua, NH3 amine. Amine double M will come. Write anionic first, then the neutral ones, then write this list. Okay. Okay, one more thing. In some of the cationic, basically you have to write EM at the last. EM at the last. See, NO positive is written as nitrosonium. NH2, NH3 positive is written as hydrazinium. Now this is neutral again. NH2, NH2, so it is hydrazine. Written as it is. Great. Great. Okay, coming back to my point over here. Those of neutral and cationic ligands are same except for water, you have to write aqua. Do remember, when there is water, you have to write aqua. Okay, for amine double M, for NH3, for CO you have to write carbonyl, for NO you have to write nitrosyl. I've given you the list over there, right? While writing the formula of the coordination and tiety, they are enclosed in brackets. You have to write them in brackets. Great. Okay, shall we proceed to the next one now? Prefixes mono, di, tetra, etc. Okay, these are there to indicate the number of individual ligands in the coordination and tiety. When the names of the ligands include a numeral prefix already, then the terms bis, tris, tetrachis are used, the ligands to which they refer being placed in the parenthesis. Example they have given you over here. One more example I can correlate with you. For example, if I say we have central metal atom as platinum. Now the ligands which I am taking, let us take chlorine over here. Okay, then we can take off ammonia and we can take iodine. Let us say that we have this particular over here. Now I told you before writing about the central metal atom, you have to write about the ligands. So what are the ligands that are present over here? For chlorine, you know, it is chlorido. For chlorine, it is chlorido. For amine, it is AMMINE. For iodine, it is iodido. It is chlorido. So if I have to write it in terms of like how many Cl, A, B, C, D, which will come first? Amine will come first. How many amine? 4 amine. So it will be tetra amine, double M will come, okay? They told you that you have to represent how many ligands are there in terms of di, tri, tetra. 4 is written, so tetra amine, then A, B, C, D, C will come. How many chlorine? 3. Tri, chlorido. How many iodine? 1 only. So iodido. And then you need to write the ligand name. Then you need to write the central metal atom name. So this is the naming for ligand. Ligand's naming. So by this way you can name the ligand as well. Now the next comes the oxidation state of the metal in cation, anion or neutral coordination and tiety is indicated by the Roman numeral. You have to write the oxidation state along with the central metal atom in the Roman numeral. Okay. Now comes the next one. If the complex ion is a cation. Okay. What it is saying? If a complex atom is a cation in this case, metal is named same as the element. Okay. Now this is we are talking about the central metal atom. Now we have studied about ligand, now central metal atom. If it is the cation, basically you have to write it as it is. Okay. For example, CO in the complex cation is represented as cobalt and PT is written as platinum. If the complex ion is anion, for example, if your complex ion has a positive charge on this, then the central metal atom is written as it is. But if it has a negative charge on it, then the central metal atom ends with suffix 8, which 8, ATE 8. Is it clear to you? Then comes, for example, if we have this particular, if we have this COSCN 4 minus 2, this has which charge? Minus 2 charge. Then if you are writing cobalt, you won't write cobalt. If it has a positive charge over here, you have written cobalt as cobalt only, but over here it will be written as cobaltate. Cobaltate. Okay, you have to write in such a way. For example, for Fe you will write it as ferrate. What? Ferrate. Similarly, if you need to write for silver, it will be what? Silver, for tin. Okay, 8 will come at the end, right? Clear? Clear, students? Shall we proceed further? Now comes the next one. See, the neutral complex molecule is named similar to that of the complex cation. It is written as it is, but only for anionic it is different. Okay, for anionic it is different. Kindly write this rule so that we can start with our very first question now. So yes, students, now let us start with the very first question of ours. Yes, I guess you have written all of these. Now let us proceed with the questions over here. Great. Okay. So the very first question in naming is K4 FeCN6 and charge is -4 overall. So what is the basic thing that we need to do? See, first of all, if there is any cation written outside the coordination sphere, you will start from left to right direction. This is your right hand, this is your left hand, from this to this direction. So you will first of all write it here. What was the first rule? The cation has to be named first. After that, ligands have to be named. After that, central metal has to be named, like this. So over here, see, for K4, you will write potassium. For K4, what you will write? You will write potassium. You need not to write the number. Okay, next is iron. Now basically Fe over here, it is written as what? What is the overall charge on this? It is -4, anionic. What I told you, you will write it as 8. You will write the suffix as 8 when it is anionic. So for iron, I already told you ferrate will be written. Yes, but after writing the cation, first of all you have to write the ligands. So the ligand over here is cyano. I have told you its name is cyano. How many cyano are there? 6. For 6 you have to write hexa. For 6 you have to write hexa, cyano. Now write the central metal atom as ferrate. And now in the bracket you will write the oxidation number of the central metal atom. Calculate the oxidation number. See, basically it has a +1 charge, 4, so it will have -4 charge. So this will have X plus cyanide is -1 into 6. Overall charge is -4. X comes out to be +2. So the charge shall be written in the Roman numerals 2. Either you can do in such a way, +4 plus X minus 6 is equivalent to 0, or you can do in such a way. Okay. This I have already written so that you don't get confused over here. It has +1 charge, it has -4 charge. I have dissociated already. Okay. Now, moving on to the next question over here. See, again it is written as what? Potassium. There is no need to write the number of potassium. It is 2, no need to write. Now you will write about the ligand. Ligand is what? Chlorine. For chlorine you write chlorido. How many chlorine? 6. So it is hexachlorido. Hexachlorido. Now what is platinum? Platinum will be written as platinum or not? Just forget it if it is written over here. Forget it is written here or not. You have to write it on your own. Potassium hexachlorido. Platinum will be written as platinum or not? You know potassium holds +1 charge. Total potassium is +2. So overall charge of here comes out to be -2. Great. That means anionic. Again, platinum is not written as platinum. It will be written as platinate. Because it has anionic. The overall charge is -2. Platinate. Now we shall write the oxidation state in the bracket. Let us calculate for potassium. See, either ways what you can do is just forget the charges on them. Just forget all the charges on them. You have potassium over here. How many potassium? 1 into 2. For platinum you need to calculate. For chlorine it is -1 into 6. Forget the charges. Overall charge sum will be 0. It is +2 plus X minus 6 is equivalent to 0. X comes out to be what? +4. So 4 will be written in Roman numerals. Is it clear to you all? Is it clear to you all? Now look up to this question over here that we have. Again, we will write. Now, forget it, okay? This I have written for your convenience. Forget it. It is potassium again. You will write the ligand. Ligand is iodide. How many iodide? 4 iodide. For it will be tetra iodide. Now it will be written as what? Mercurate. Mercury is there, so you will write mercurate. Mercurate. Now write the oxidation state in brackets. See, for potassium it is +1. How many potassium? 2. Plus for Hg it is written as X. For iodine -1 into 4. Overall charge will be 0. +2 plus X minus 4 is equivalent to 0. X comes out to be +2. So you will write it in such a way. Is it clear to you all? Kindly write the 3, all of these 3. Okay, let us see the next that we have. The next one is here. Now again, this is potassium. There is no need to represent the number for the cation. Potassium. Then we have what? We have NO2. NO2 is basically nitro. How many nitro? Ma'am, 6 nitro. So basically it will be hexanitro. Now what will be the central metal atom? See, basically if it has positive charge, obviously it will have minus charge. If it is +3 charge, it will be -3. Anionic. So it will not be written as cobalt. It will be written as cobaltate. Cobaltate. Now you have to write the oxidation state in bracket. Again, see, forget the charges that you have written. The charge, see, why I have written -3 in order to see that whether it is an ionic or cationic sphere. Okay. Now for potassium, it is +3 charge because it is +1 into 3 +3. For cobalt, you need to calculate. Now you again have NO2 over here. NO2 has which charge over here? Now you see, students, basically, if you see, NO2 basically has -1 charge into 6 is equivalent to 0. X minus 3 is equivalent to 0. X comes out to be +3. So you will write it in Roman numerals, right? Now let us see this case. Now this is sodium. We will write sodium over here. Now you have two things over here. Now you have two things over here. Two kinds of ligands over here. One you have is cyano. Another one is NO, which is nitrosyl. This is cyano. This is nitrosyl. C comes first. Now you will say, ma'am, 5 are written over here. Pentite starts with P. No. You have to see the ligand's name. Cyano and nitrosyl. C will come first. How many cyano? 5. So penta cyano, then will come 1 nitrosyl, so nitrosyl. Now see, if it has +1 charge, total 3, so +3 charge, it will have -3 charge, and ionic one, so it will be written as ferrate. Ferrate. Now what will be the oxidation state? See, basically, forget the charges on them. Forget the charges on them. Na has +1 charge. How many Na? 3 Na. Plus Fe you need to calculate. For Cn, you know it is -1. You should know for Cn it comes out to be what? -1, students. Is it clear? For NO it is 0 charge is equivalent to what? 0. Now +3 plus X -5 is equivalent to 0. X comes out to be +2. So the oxidation state comes out to be +2. Great. Now let us see the next one. Again, we don't have any cation, so we will start from ligand itself, right? We have amine over here, AMMINE. And we have chlorido over here. है ना? So A comes first. That means how many amine? 2. So it is written as diamine. How many chlorine? 4. So it is tetrachlorido. And then comes out to be, is there any charge present on this? No, neutral. So you will not write platinate. Now you will write platinum. Only platinum, because there is no charge. Only platinum. Write the oxidation state over here. For platinum, take it as X. For ammonia, you know it is 0 charge into how many ammonia? 2. Plus Cl has -1 charge. How many Cl? 4. Charge sum will be equivalent to 0. X plus 0 minus 4 is equivalent to 0. X comes out to be what? +4. So the oxidation state is written in the Roman numerals. Is it clear to you all? Shall we proceed further? Kindly write it down. Kindly pause the video and then write it down. Okay, now let us see the next question that we have. Now again, see, CO, cobalt. What are the ligands over here? Ligands are, ma'am, amine, written as AMMINE, and this is chlorido. So according to ABCD, amine comes first. How many amine? 3 amine. So it is triamine. It is triamine. And how many chlorine? 3. Again, trichlorido. Now it is neutral species, so you won't write cobaltate. In anionic, you write it. Over here, it will come as to cobalt. Now, oxidation state in bracket. For cobalt, we will take it as X. For ammonia, we know it is 0 charge into 3 plus Cl, we know it is -1 charge. How many Cl3 is equivalent to 0? So X comes out to be +3. That means oxidation state comes out to be 3 over here. Is it clear to you people? Now let us see again over here. We have Cl as our ligand, so it is chlorido, and we have ammonia that is written as amine over here. A comes first, so we shall name it ligand the first. Two amine are there, so it is diamine. So it is diamine. 2 chlorine, so it is dichlorido or dichloro also you can write. Okay. Then comes out to be, will it be platinate or platinum? Ma'am, platinum. Why? Because there is no charge over here. It will be platinum. You have to write the oxidation state in brackets. So for platinum, let it as X. For Cl, you know it is -1. How many Cl2? Plus for ammonia, it is 0. It is equivalent to 0. X comes out to be +2. So the oxidation state comes out to be 2 over here. Is it clear? Is it clear to you all? Kindly let me know if it is clear to you all. Now comes a different kind of question. Student. Over here, we have anion written over here, and this is cation. See, Cl has -1 charge. How many Cl? -3. So this will have +3 charge. Now this is cation in this case, and this is anion in this case. If the ionizable ion is written in front, then it is cation and it is anion. Now if it is written first, it is cation, it is anion, right? Now we shall name it first. First of all, cation is written, then the sapphire, and then the anion, left to right. Now we will name the ligand first. It is amine, 6 amine, so it is hexaamine. Hexaamine. Now I told you in the case of only and only in the case of anionic, that means negatively charged, you will write 888, but not in positive and neutral. So it is written as cobalt. Now write the oxidation state in bracket. Cobalt X plus for ammonia it is 0 into 6. Now overall charge will be +3. So X comes out to be +3. You can solve in either of the manner, by all together calculating and the sum shall be equivalent to 0, or by the charges by ionizing them, right? Now you have to write about Cl. Again, Cl is chloride, so you will write directly chloride. In cations and anions, there is no need to mention that how many number of anion or cation are present over there. Is it clear to you all? Kindly write it down so that we can move on to the next naming. I'm giving you a minute, kindly write it down. Shall we proceed further? Yes. Now moving on to the next part. Again, we have this case over here. How many chlorido? 4. So it is written as tetrachloro or tetrachlorido. Now anionic, so basically it will be what? Nickelate. Not nickel, it will be nickelate. Now write the oxidation state in bracket. For nickel, let us say it is at X. Chlorine has a -1 charge into 4 chlorine, and the overall charge is -2. X minus 4 is equivalent to -2. X comes out to be +2. So the oxidation state over here comes out to be +2. Great. Now let us see for this. Now I told you for water you have to write aqua. For water you have to write aqua. For Cl you will write chlorido. Now see. First of all, ligands. A starts. A is alphabetically initially comes first. So 4 refers to as tetra. So tetra, aqua, dichloro or dichlorido. Now chromium. Now see basically what happens. Cl is a -1 charge, so it will have +1 charge. Cationic. So you will write chromium as it is. Chromium. Write the oxidation number of the central metal atom over here. Chromium has X. Now water is neutral, so 0 charge into 4 water plus Cl has -1 charge into 2 Cl. Overall charge is what? +1. So basically X minus 2 is equal to +1. X comes out to be +3. So written in bracket, right? Now comes this ion, that is Cl, that is chloride. So this shall be the name. This shall be the name. Kindly write it down. Now this is the most important one and a different kind of question that I have taken over here. See, basically here, first of all, we have, when we have hydrogen in terms of ionizable ion. When we have hydrogen in terms of ionizable ion, then the central metal atom ends with -ic. Okay. Now let me tell you how. See, how many chlorine? First of all, write as it is. Just forget that you are representing hydrogen over here. Forget it. You in the case of hydrogen, just forget it. You have to write what? How many Cl? 6. So it is hexachlorido. Now if you will write platinum, but it will not be platinum. It will be platinic. which represents that hydrogen is present as an ionizable ion. Then you will write the oxidation state over here, and at the last you will write acid, because we have hydrogen as the ionizable ion. Now over here for platinum it is X, for chlorine you know it is -1 into 6. Now what shall be the overall charge? You can clearly see if it has a +1, how many hydrogen? +2. So it will have how much charge? -2. So it is X minus 6 is equals to -2, X comes out to be +4. So the oxidation state comes out to be 4 over here. Is it clear? Kindly write it down. Kindly write it down, students. Okay, yes. Now moving on to the next question. Now comes your homework question. This is your question number 2 as a homework. This is your question number 3 as your homework. And this is your question number 4 as your homework. Is it clear? Is it clear? Kindly pause the video and you have to write its answer in the comment section. Question first, question second, question third, question fourth. Question first was taken initially, right? So you have to write its answers in the comment section. Pause the video and write the questions. Other than this, students, there are some of the cases taken from NCERT directly. There are 3 cases that have been given in your NCERT. So I've written over here. The very first case is this one. See, the naming for this now you can easily do. They have written its name. Their name will be what? This is basically aqua. This is basically amine. So AM first comes. So how many amine? 3. So triamine. Then comes out to be how many aqua? How many water? Triaqua. Then is chromium. Okay. And then its charge will be what? Because it has holes +3 charge. So it is oxidation state will be chromium. Let us say it X. For ammonia it is 0. For water it is 0. And for overall charge is 3. So oxidation state is 3. And then comes out to be chloride, which is present outside. So now you are familiar with this. They have explained you all together in this particular paragraph all of the things which I have told you already. Great. Now the next question that is being solved in the NCERT itself is this one. Now this is basically what? This is basically what? See, it is your En. It is your En. How many En? 3 En. 3 En. Now I have told you En is what? Ethane 1,2-diamine. It is En. Now ethane 1,2-diamine. There is a word di already present inside. So you won't use di again. You will now use, it is 3. So you will do tris. Instead of using tri, you will do tris. Because ethane 1,2-diamine already contains di. So if you have to write it, you will write tris ethane 1,2-diamine. Then comes central metal atom as cobalt and its oxidation state. And at last it will come out to be sulfate. Great. Now comes the last NCERT in text part that is given to you as this one. So they have written it as diamine silver. Okay, and then is dicyanide or cyano you can write, and then is argentate, and there is oxidation state. Is it clear? Now students, next homework questions. These are the other questions again from the NCERT that I have given you. Example 9.2, 9.3, in-text question 9.1, 9.2, and NCERT back exercise 9.5, 9.6 and 9.7. This you have to do as your homework, right? I hope so. Now these namings, it will be clear to you. Now one more naming is left, that is naming of bridging complex, that we shall do in the next lecture along with the next topic further. I hope so this lecture was clearly understandable and you are able to now name the different and the complex to complex organic compounds. Yes. So we shall meet in the next lecture. I want you all to solve the practice sheet of the DPP that you have. Also the homework questions that I have given you over here, so that you can practice more and more questions and the concept will be automatically more clear to you. So we shall meet in the next lecture. Till then, keep smiling, keep learning. Thank you so much and have a good day.